Imagine a scene worthy of a high-budget sci-fi blockbuster, or perhaps a page torn from an ancient prophecy about the end times. You step outside in the dead of night, at an hour when the world should be wrapped in sleep and darkness. But instead of the familiar black velvet of the sky, sprinkled with the sharp points of distant stars, you see something that makes your brain stutter. The sky is washed in a ghostly, milky white, unnatural light. Shadows from trees and buildings stretch across the ground so sharply it looks like high noon. Streetlights seem like dim, useless matches against the glow of the object hanging above the horizon. This isn't the moon. This is a tailed celestial body that rivals the brightness of stadium floodlights. And if you believe the boldest predictions, by day, when the sun is at its zenith, you might be able to see this object right next to our star just by shielding your eyes with your hand. This is exactly the apocalyptic and majestic picture painted by today's news headlines. The internet is practically exploding. Bloggers, TikTokers, and social media admins are competing to invent the loudest superlatives. They promise us a second sun. They promise that night will turn into day. They tell us NASA specialists are in shock, that scientists are hiding the truth, that ancient calendars predicted this exact event. It is a classic textbook scenario of global information hysteria. It grips humanity with enviable regularity every time a sufficiently large, reflective celestial body approaches Earth's orbit. The psychology behind this is clear. We, people of the 21st century, tired of the grind, the crises, and the digital noise, are starving for a miracle. We want the heavens to open up and show us something that makes us forget about exchange rates and political bickering. But where, in this flood of clickbait, does fantasy end and harsh astrophysics begin? Today, we are not giving in to emotion. We are setting aside mysticism and prophecies. We are picking up a calculator, star charts, and most importantly, dry, emotionless photometric data. Our task is to investigate. Are we truly standing on the threshold of the century's greatest light show? Or is this just another soap bubble inflated by search engine algorithms that will burst, leaving us in the dark of disappointment? To understand the heart of this debate and evaluate the reality of these forecasts, we first need to agree on our terms and tools. In astronomy, the brightness of objects isn't measured in watts, lumens, or candelas. Astronomers use the magnitude scale. This is a unique system that can confuse the uninitiated because it is counterintuitive. It works backward. The lower the number, the brighter the object. Furthermore, this scale is logarithmic. A difference of just one magnitude means a change in brightness, not by a few percent, but by 2.5 times. A difference of 5 magnitudes means a difference in brightness of 100 times. Understanding this is critical for our conversation. Let's set some benchmarks on this scale to give us a coordinate system. The sun, the absolute champion of brightness in our sky, the king and god of the solar system, has a magnitude of -27. That is monstrous energy, capable of burning your retina in a fraction of a second. The full moon, our night lantern, is roughly -12.5. That's bright enough to read a book by, but it is 400,000 times dimmer than the sun. Venus, the famous morning star, shines at about -4. Jupiter and Mars can reach -2. The brightest star in the night sky, Sirius, is -1.46. And the human eye. In ideal conditions, far from city light pollution, we can distinguish faint sparks down to +6. That is the limit of our biology. And now a new variable crashes into this neat equation: a comet. Current computer models are assigning it a magnitude of -10, -12, or even higher. Think about those numbers. -10. That means the object would be hundreds of times brighter than Venus. It means it would be comparable to the full moon, but concentrated into a much smaller point, creating incredibly high surface brightness. If these models are correct, we really will get a second sun. Dimmer than the original, sure, but bright enough to cast shadows and be visible in the daylight sky. Sounds like a fairy tale? Like the ramblings of a mad astrologer? Don't rush to conclusions. The history of science knows examples where such seemingly impossible predictions came true with frightening accuracy. To find proof, we need to rewind the tape of history. Remember 1965, comet Ikea-Seki. It appeared out of almost nowhere and put on a show that eyewitnesses remembered with awe for the rest of their lives. At the moment of perihelion, its closest approach to the sun, it flared up to an incredible magnitude of -17. To give you a sense of scale, that is dozens of times brighter than the full moon. It was so bright it was visible at noon, right next to the blinding solar disk. People in Japan walked out into the streets, blocked the sun with a hand or the corner of a building, and saw a bright white comma right next to it. And its tail, curved by magnetic fields and solar wind, slashed across the entire sky like a giant searchlight, like a celestial sword. Japanese observers described it in their diaries as a dagger cutting the heavens. This isn't a myth. This isn't a legend from medieval chronicles. This is a documented, photographed, scientific fact of the 20th century. It means the physics of our universe allows for such monsters. It means, theoretically, our current guest could repeat this success. It is this hope, backed by historical precedent, that fuels the current hype. People want to touch greatness. But here enters the main, cruelest law of cometary astronomy, once ironically formulated by the famous comet hunter David Levy. He said, "Comets are like cats. They have tails, and they do precisely what they want." Predicting a comet's brightness is like trying to predict the stock market during a global crash, or guessing the weather at a specific point in the ocean a month from now. We are not dealing with a solid, predictable rock like an asteroid or the moon, which have constant albedo, reflectivity. We are dealing with an active, living, boiling object. What is a comet? Textbooks say dirty snowball, but that's too soft a definition. It is an icy mountain packed with dust, rocks, frozen carbon monoxide, methane, and cyanides. While it flies through cold space, it sleeps, but as soon as it approaches the heat, chaos begins. Its brightness depends not on how big it is, but on how much dust and gas it spews into the surrounding space. It must create a coma, a giant cloud around itself that acts as a reflector of sunlight. And this is where the lottery begins. The outgassing process depends on thousands of factors. How will the nucleus heat up? Evenly or in spots? Are there cracks on the surface through which geysers of gas will erupt? Or will the crust bake under radiation and seal the volatiles inside, turning the comet into a dark boulder? Will the nucleus suddenly disintegrate, causing a colossal flare-up? Or will the comet quietly sizzle away? We look at the forecast graph on a computer monitor and see a beautiful, smooth curve shooting upward. But the comet doesn't know our graphs. It doesn't obey our wishes. It obeys the chaos of thermodynamics and hydrodynamics. The intrigue of the current moment lies in a unique physical phenomenon that might play into our hands. This phenomenon is called forward scattering. It's a term from atmospheric optics. Imagine driving a car in the fog, and another car is driving toward you. When it's far away, its headlights just shine. But as it passes you, and you look at its light through the fog, the brightness spikes dramatically. Everything around begins to glow. This happens because microscopic water droplets or dust particles scatter light primarily forward in the direction of the beam. The same thing can happen with our comet. If it passes between Earth and the Sun and dumps enough dust, the sunbeams passing through that dust trail will scatter toward Earth, amplifying the comet's brightness hundreds of times. This is the effect that turned Comet McNaught in 2007 into an unforgettable spectacle. Right now, as we discuss this, our celestial object is undergoing its main stress test. It is approaching the invisible line astrophysicists call the snow line, or the zone of active sublimation. The star's thermal radiation is stripping away its layers, penetrating deep, waking up ancient ice that has slept for billions of years. And the real-time data coming from telescopes is extremely contradictory. On one hand, we see huge potential. The nucleus seems large and active enough to produce a massive ejection. Spectral analysis shows plenty of volatile substances. On the other hand, we see strange, rhythmic flickering that makes professional skeptics frown. These flickers could be a sign that the nucleus is unstable, that it is ready to fall apart before it even reaches the main stage. Is this truly a new Ikea Seki, ready to set the sky on fire and enter history books? Or is this a cosmic con artist, a great fake comet that will flare for a second, give hope, and vanish, leaving us in the dark with our broken expectations and the mockery of skeptics? The bets in this celestial roulette have been placed, and they are incredibly high. This isn't just about a pretty picture, it's about testing our ability to understand and predict processes in near space. We will either get a night that turns into day, a generational event, or we will get a harsh but useful lesson on how ruthlessly reality can treat human expectations. We are standing in the front row, the curtain is rising, but no one, not even the director of this play, the sun, knows the ending of the first act. To separate the grains of truth from the chaff of information noise, we need to come down from the clouds and look under the hood of this cosmic event. We are moving to the second phase of our investigation, the mechanics of the process. Why should a dirty chunk of ice flying in a vacuum glow at all? And why did this specific object cause a storm of predictions comparable only to medieval expectations of a messiah? To answer these questions, we have to dive into three disciplines: celestial mechanics, the physics of small bodies, and atmospheric optics. Let's start with our hero's origin. The dossier we have suggests this is a classic sun-grazing comet. It's not just a random passerby cutting through our neighborhood. This is a body moving on an extreme suicidal orbit. Its perihelion, the point of closest approach to the star, is at a distance that, in cosmic terms, is intimate. The comet will pass through the sun's outer atmosphere, through the corona, where temperatures are measured in millions of degrees. But don't assume the temperature is what makes it shine. Comets are cold bodies. They don't emit their own light like stars. They work like mirrors. Let's break down the physics of comet light. Imagine a piece of coal, a black, porous, dirty lump of anthracite. That is roughly what a comet nucleus looks like up close. Its albedo is negligible. It reflects only 3 or 4% of the light hitting it. That is darker than fresh asphalt. So how does this black cobblestone turn into a second sun? The answer lies in the transformation of matter. As the nucleus nears the snowline, solar heat triggers sublimation. Ice, entombed in the comet's depths for billions of years, instantly turns into gas, skipping the liquid phase. This gas bursts out like steam from an overheated boiler, ripping the surface and dragging billions of tons of microscopic dust with it. This is where the magic happens. The comet stops being a solid body and becomes a giant cloud. The black nucleus hides inside the coma, a glowing sphere of gas and dust that can be larger than Jupiter or even the sun in size. And this coma works like a perfect diffuser. Solar photons hit the dust particles and bounce in all directions. More dust means a larger mirror, which means a brighter comet. But there is a nuance that spawned all these sensational headlines. This nuance is the forward scattering effect. This is the key moment of our investigation, so let's dwell on it. Imagine standing in a dark room and someone shines a flashlight into your face through a cloud of cigarette smoke or dust. The smoke begins to shine unbearably bright, creating a halo around the light source. This is backlighting. In astronomy, it works like this. When the comet is in a straight line between Earth and the sun is shining on its back. If the comet dumps enough dust at that moment, the sunbeams passing through its tail and coma will be amplified dozens, maybe hundreds of times. It is this effect that supports the predictions of magnitude -10 or 12. Astronomers calculate the phase angle. When this angle approaches 180 degrees, mathematical models show an explosive growth in brightness. It's not magic, it's geometry. But the problem with these models is that they assume ideal behavior. They assume the comet will obediently release dust at exactly the right moment. Now, let's look at the historical precedent that serves as the foundation for all current hopes. Our star witness for the defense, the Great Comet of 1965, Ikeya Seki. Its story is almost a ready-made script for a Hollywood drama. It was discovered by two Japanese amateur astronomers building telescopes with their own hands. No one expected much until its orbit was calculated. It turned out it would fly just 450,000 kilometers from the sun's surface. That is half the radius of the star itself. On the day of perihelion, October 21, 1965, Ikeya Seki entered the death zone, and instead of evaporating, it flared. Forward scattering worked at full power. Its magnitude hit -17. To understand the scale, that is 60 times brighter than the full moon. Observers worldwide reported seeing it with the naked eye at noon, just by blocking the sun. Next to the golden disk of the sun hung a silver comma with a curved tail. It was a biblical spectacle. But triumph came at a price. Gravity and thermal shock tore the comet's nucleus into 3 pieces. It became the brightest, but it died as a single entity. Skeptics, however, point to another example that cools the enthusiasts' ardor: Comet Kohoutek, 1973. It was dubbed the Comet of the Century before it even arrived. The media went crazy. Newspapers printed star charts, people bought telescopes, forecasts promised magnitude -10, and in reality, it was a dim, barely visible smudge that you could only spot with binoculars, and only if you knew where to look. Why? Because the comet turned out to be old. Its volatiles were depleted or covered by a crust of dust baked by cosmic radiation into a hard shell. Solar heat simply couldn't punch through to start the reaction. Comet Kohoutek became synonymous with a massive astronomical letdown. So, what is the main problem with predicting brightness? Why can we predict an eclipse down to the second 1,000 years in advance, but can't say how a comet will shine next week? The problem is, we don't see the nucleus. Even in the most powerful telescopes, the nucleus is a point smaller than a pixel, hidden behind the dense veil of the coma. We don't know its size. We don't know its density. We don't know its chemical composition. We don't know the surface terrain. Is it a monolithic rock, or a loose pile of rubble held together by weak gravity? There is another factor rarely mentioned in popular articles, but critical for the observer: the difference between integrated brightness and surface brightness. When they tell us -10th magnitude, we imagine a point as bright as a laser. But a comet isn't a point. It's a diffuse object. Its light is smeared over a large area of the sky. If you took the light of the full moon and smeared it across the entire sky, the sky would get a bit lighter, but you wouldn't see a bright object. The same can happen here. The comet might have huge total brightness, but because it's stretched into a long tail, it will look like a ghostly glow, not a bright star. Against a daytime sky, which itself is very bright, such a smeared object might simply dissolve, becoming invisible due to low contrast. Thus, the mechanics of the upcoming event is a complex equation with a dozen unknowns. We have geometry promising a second sun. We have the history of Ikea Seki proving it's physically possible. But we also have the physics of a dirty snowball, warning that the nucleus might be too dense to steam or too loose to survive. We are standing in front of a closed door behind which a chemical reaction is taking place, and we will only know the result when the door opens. Right now, as the comet races toward its climax, astronomers worldwide aren't watching for pretty pictures. They are watching outgassing graphs. They are looking for signs that the crust has cracked. They are looking for jets, streams of gas acting like thrusters that can spin the comet, tearing it apart with centrifugal force. The Ikea Seki scenario is a catastrophe that became beautiful. The Kohoutek scenario is survival that became boring. Which path will our guest choose? The physics is in motion and it cannot be stopped. The countdown is not in days but in hours. We have reached the climax of our investigation. All bets are placed, all forecasts voiced, and telescopes are pointed at one spot in space. The moment of truth arrives, what celestial mechanics calls perihelion. These are the few hours that decide the fate of the celestial body and the fate of our expectations. Right now, the myths of a second sun must either materialize into blinding reality or crumble into dust, leaving only digital noise. We are entering the phase where the main witnesses are not bloggers, but the coronagraphs of space observatories and the laws of optics, which cannot be cheated. Let's return to the main accusation science levies against clickbait. We were promised the comet would be visible by day. We were promised magnitude -10. But what does that mean practically for an observer standing on Earth under a thick layer of atmosphere? Here we face the fundamental concept of contrast. Imagine lighting a candle. In a dark basement, it seems dazzling. But take that same candle outside at noon, and you won't even notice it. The daytime sky has huge surface brightness. For an object to be seen against it, it must be either point-like and incredibly bright, like Venus, or have a surface brightness exceeding that of the blue sky. And here lies the trap. A comet passing near the sun is not a laser beam. It is a cloud. A vast, rarefied cloud of dust and gas. Even if the total brightness reaches -10, that light is spread out. The surface brightness might be below the eye's sensitivity threshold against daylight. We get a paradox. Instruments detect a colossal flow of energy. Mathematically, the comet is brighter than the full moon, but the eye doesn't see it. It dissolves in the atmospheric glare. The second sun turns out to be a ghost. This is reality's first strike against inflated expectations. But the most interesting action isn't in Earth's atmosphere, but up there, in the immediate vicinity of the star. The judge is the SOHO Space Observatory. Its cameras artificially block the solar disk, creating an eternal eclipse to see the corona. That is where our comet is flying, into that black circle. Astronomers watch the refreshing images with bated breath. And what do they see? A struggle between two trends. On one side, forward scattering makes the dust shine. On the other, the destructive force of heat takes over. The plot twist is that the comet's death might look brighter than its life. When the nucleus can't withstand the thermal stress and breaks apart, an outburst occurs. Internal ice reserves are instantly exposed and sublime explosively. At that moment, brightness can jump by 5 or 10 magnitudes in hours. This is agony, the death scream of a celestial body. And the irony is that we on Earth might mistake this death flare for the promised show of the century. The internet explodes again. Look, it's brightening. The predictions came true. But professionals look at the charts and realize this isn't triumph, it's the end. Peak brightness coincides with destruction. Let's analyze this physically. The nucleus enters a zone where solar radiation is thousands of times stronger than on Earth. Material evaporates faster than gravity can hold it. Light pressure kicks in. Photons, those massless particles, turn into a tangible wind at these power levels. They blow the dust away. The tail gets distorted, torn into fibers. We see chaos, not structure. If Ikea Seki survived this in 1965 due to its density, our current hero is likely looser. At this moment, the second sun transforms into the headless horseman. The center of condensation, that bright point, disappears. It turns into an elongated foggy streak. Brightness drops as fast as it rose. The show ends before it begins. Those waiting for nightfall to see a tail across half the sky are disappointed. The dust cloud, deprived of its source, quickly disperses. It becomes too transparent to reflect light. However, the defense has a case. Science tells us that even this scenario is incredibly valuable. We are observing a crash test arranged by nature itself. We learn the breaking point of cometary matter. We understand that brightness predictions based on simple power laws don't work for extreme encounters. Every such failure refines our models. We learn to distinguish long livers from disposable fireworks. There is also a biological aspect the sensationalists forget. Looking at a comet near the sun is dangerous. Even at magnitude -10, it's only a couple of degrees from a star shining at -27. Trying to spot the miracle with the naked eye, or worse binoculars, can end in retinal burns and blindness. The reality is that the year's brightest show might be available only to robots, space telescope cameras that have no eyes to burn. For us, the show becomes waiting for JPEGs on a website. The gap between seeing it from the balcony and seeing it on a NASA screen becomes insurmountable. The culmination of this comet's story is a lesson in optical illusion. We interpret data how we want. We confuse absolute brightness with apparent brightness. We forget atmospheric extinction. When an object is low on the horizon, its light must pass through a thick, dense layer of air. The atmosphere acts like a filter, eating up to 90% of the light. A brilliant comet shining like a spotlight in space turns into a dull, reddish smudge near the horizon. Thus, the verdict is harsh, but fair. The second sun promises were based on correct physics, forward scattering, but ignored limiting factors, surface brightness, atmospheric absorption, daytime contrast, and the nucleus's structural integrity. We witness classic survivorship bias. We remember the comets that survived and became great, and forget the thousands that promised greatness but crumbled to dust. Our object likely joins the latter, but don't despair. Even in death, it offers a unique spectacle. We see solar wind tearing apart matter frozen since the solar system's creation. Is that not a miracle worth watching? In the final part of our investigation, we step away from telescopes and look at the situation philosophically. What does this chase for light records say about us? And is there a chance a real monster will visit us in the future? So, the dust raised in the solar corona has settled, scattering into interplanetary space. The informational dust raised by headlines has also begun to settle. We close the case file on another comet of the century, but before archiving it, we need a debrief. We must answer questions more important than a fleeting spectacle. What did we actually learn? Was the game worth the candle? And why do astronomers consider this a triumph of science despite the public's disappointment? The first and most important conclusion concerns the value of a negative result. To the public, if the comet didn't turn night into day, it's a failure. To science, it's a priceless dataset. The comet's death told us more about its internal structure than if it had just flown by as a pretty dot. The fact that the nucleus crumbled allows us to judge the density and chemical composition of the solar system's primordial matter. We confirm that comets aren't uniform balls. They are layer cakes where ice alternates with organics and silicates. Analyzing the gases released gave us clues about the formation of our planet 4.5 billion years ago. We learned whether Earth's water was delivered by comets or has a different origin. Every failed comet is a page from a history book we are just starting to read. The second aspect is our addiction to sensations. This story exposed a deep psychological problem. We have become intolerant of the normal flow of things. We need hyperbole. If it rains, it's the storm of the century. If it's a comet, it must be brighter than the sun. This inflation of expectations means we stop appreciating the beauty of reality. We look at a beautiful, rare object visible in binoculars and say, "Meh, that's not what TikTok promised." Science teaches humility. It says, the universe is not obligated to entertain us. The comet doesn't fly so we can shoot a cool video. It flies because it obeys Newton and Kepler. The forward scattering effect worked exactly as physics dictates, not as marketers hoped. Brightness increased, but observing conditions were harder. This is a lesson in critical thinking. Next time you see a headline about a green comet destroying civilization, remember this. Remember the difference between integrated and surface brightness. Remember the treacherous atmosphere, and look for primary sources, not reposts. But let's look to the future. Does this mean we'll never see a true great comet? Of course not. Statistics are on our side. The solar system is surrounded by a giant reservoir of icy bodies called the Oort cloud. Trillions of potential comets drift there. Some are not a few kilometers wide, but dozens or hundreds. Sooner or later, gravity from a passing star will nudge one of these monsters our way. Remember Comet Hale-Bopp in 1997. It didn't get extremely close to the sun, but its nucleus was so huge, 60 kilometers wide by some estimates, that it shone for 18 months. It was visible even in megacities. Such giants arrive rarely, once in decades or centuries, but they are inevitable. Our current hero was just a scout, a small, loose courier who burned up completing its mission, but others stand behind it. And when the true comet of the millennium arrives, we won't need internet headlines to know. We will simply walk outside, look up, and freeze in awe. Furthermore, technology isn't standing still. We are entering an era where comet watching isn't just for ground telescopes. Spacecraft like Parker Solar Probe or Solar Orbiter get closer to the sun than any planet. They see what is hidden from us by the blinding glare. In the future, we might send interceptor missions. Imagine a probe landing on a comet, flying to its death, broadcasting data until the last second before vaporizing with it. That will be a show eclipsing any sci-fi movie. We will stop being passive observers of shadows on a cave wall. We will become participants in the experiment. The final conclusion is philosophical. Why was seeing this second sun so important to us? Because humans are creatures seeking light in the darkness. A comet is a symbol of change, of movement, a sign that our world is not static. We live on a small rock hurtling through the void, and when another wanderer flies by, we feel we aren't alone on this mechanical carousel. The disappointment that the comet wasn't so bright is actually a longing for a miracle. But the miracle exists. It lies not in brightness, but in knowability. The miracle is that apes who recently feared thunder can now calculate the orbit of an ice block billions of kilometers away. The miracle is that we know why it glows, why it has two tails, and why it dies. We replaced fear of celestial omens with an understanding of astrophysics, and that is perhaps humanity's brightest achievement, shining stronger than any comet. With that, we close our case. Don't delete your star map apps. The cosmos is vast, and something interesting is always happening. Perhaps right now, as you listen to this, somewhere in the cold depths beyond Neptune, a new icy giant is beginning its fall toward the sun. It has no name yet. It isn't visible in the most powerful telescopes, but it is on its way. And when it arrives, we will be ready. We will meet it not with fear and superstition, but with spectrometers, high-resolution cameras, and a thirst for knowledge. Look up more often. There, among the stars, our history is written. See you in the next orbit.